this part. And this expression is quite similar to the expression we have derived in semester 3 class in advanced econometrics or annual time series. If you ignore 4, it will be the same as in the case of annual time series you have got in 3rd semester. Okay, so apparently it is right. You are right. So this is the expression for quarterly data. If it follows autoregressive of order 1, we are focusing purely on the seasonal part, ignoring the non-seasonal part. So you can easily generalize this expression for any frequency, any seasonal frequency. So YTS, this is the expression for quarterly data. So you can generalize this expression for seasonal frequency S in this way. YTS is equal to, this is the AR1 form.
Sir, onake join hote jayche.
So for seasonal frequency S, so this is the conventional form of AR1, and after expressing this form by following the same rule, you will get phi 1t. Just compare, just put here S instead of 4. Okay, so you ultimately get the expression for, so you also have to change this part. It becomes T minus J into S. Okay.
Sir, joining request আসছে.
Now look at this expression. This is the general solution for first order stochastic difference equation with seasonal frequency S. And the first element in the right hand side denotes the homogeneous solution, and the second element denotes the challenge solution to capture the stochastic component in the difference equation. Now, let we remember the concept of stationarity. The process will be stationary when it is converging towards its long run average. And it will be converging only when this component tends to 0 as t tends to infinity. Because if we take the mean value of this, if we take expectation on both sides, the expected value of the second component becomes 0 by assumption. So you have got this. So expected value of y will be 0 only when this part tending towards 0 as t tends to infinity. And it will happen only when phi 1s is less than 1. So this is the stationarity restriction for seasonal time series of order autoregressive of order 1. So if a seasonal time series follows AR,
joining request,
then this series will be stationary only when phi 1s less than 1. What is phi 1s? Phi 1s again is the coefficient for AR1 component in the seasonal time series. Okay, so in finding out whether a series contains unit root or not, we always need to focus on the coefficient for AR1. If the coefficient for AR1 is less than 1, then we can say the series will be stationary even in seasonal variation as well. Now you can generalize the expression for seasonal autoregression of order P. So up to this, we have restricted to SR1. Seasonal autoregression of order 1 and seasonal autoregression of order 1 can be looked at in this way to find out whether it is stationary or non-stationary. Now suppose we have autoregressive of order P on seasonal part only, ignoring the non-seasonal part. So it looks like YTS is equal to phi 1S YT minus 1S plus phi 2S YT2 minus T minus 2S. In this way, you have phi PS YT minus P into S plus epsilon TS. That is, how do we get it? If we put 0 in our earlier stochastic autoregressive process in non-seasonal part. If we put the non-seasonal part 0, then you can get this component. Similarly, for the moving average, and you can get specific expression for moving average of order 1, moving average of order 2, moving average of order Q. Just try to find out this by yourself. All. আমি তোকে একটু পরে ফোন করব, আমি আধ ঘন্টা পরে করি, আধ ঘন্টা পরে করছি, আধ ঘন্টা পরে করছি, নাকি এখনই দরকার? একটা ক্লাস নিচ্ছে, শেষ করবি? হ্যাঁ হ্যাঁ হ্যাঁ, শিওর শিওর। আচ্ছা আচ্ছা, ঠিক আছে। আচ্ছা আচ্ছা, ঠিক। Have you got these expressions? Stochastic seasonal moving average of order 1, this seasonal moving average of order 2, seasonal moving average of order Q in expanded form. Similarly, for the ARMA case, seasonal autoregressive moving average of order PQ. In all cases, we have ignored the non-seasonal part. We are focusing only on the seasonal part. Sarima PDQ. Now you can incorporate some deterministic element as well in the Sarima expression. So this is the seasonal autoregressive moving average, autoregressive integrated moving average process of order PDQ in compact form in this way. If we want to incorporate the deterministic part, that is a series may contain deterministic trend, or it contains a drift parameter. So in that case, you can add alpha plus beta into T plus sum of gamma I di. This capital Di indicates the seasonal dummy. We have mentioned seasonal dummy when we discuss the deterministic seasonal part. So up to this, alpha plus beta into T plus sum of gamma I di, these are the deterministic component in seasonal autoregressive integrated moving average process. So the left hand side autoregressive part integrated part, moving average part. And additionally, we have considered here the deterministic part, because in reality, a particular series may contain deterministic part as well as the stochastic part. Okay, so when we consider the actual behavior of a time series, we need to take into account both the stochastic part as well as the deterministic part. So in that case, you can incorporate the deterministic part like this. This is the constant term alpha indicating the drift parameter, beta into t, the deterministic trend parameter, and this part, sum of gamma I di, it indicates the seasonal variation in deterministic component in terms of the seasonal dummy. And the last part denotes the moving average component of order Q in Sarima PDQ. Okay? Follow.
স্যার আমরা এখানে নন সিজনাল পার্টটা নিচ্ছি না, তাই তো?
হ্যাঁ, নন
তার
সিজনাল
মানে ওই
বাঁদিকের যে স্মল পি কিউ ছিল সেটা আমরা বাদ দিয়ে দিচ্ছি, আমরা শুধু বাম দিকের পার্টটাকে নিচ্ছি।
ঠিক আছে স্যার,
কারণ because the behavior of non-seasonal part is similar to the behavior of annual time series. So in annual time series, what we have got is exactly equal to the non-seasonal part here as well. Okay, so the additional aspects we have to take into account the seasonal components, specifically the seasonal part of the series. For that reason, we focus here only on the seasonal part, ignoring the non-seasonal part. Okay.
Okay, sir.
You can write down these expressions in expanded form at home. So to save time, we do not expand this part. So you can expand independently as you have expanded the expression earlier by considering the non-seasonal component as well. Okay. Now then move into the random walk case. What is random walk? In the non-seasonal time series or in annual time series, we have defined random walk if the coefficient of AR1 is equal to 1. Okay. So we have used the similar concept here. In the case of seasonal time series, this is the expression for AR1. YTS is equal to phi 1s YT minus 1s plus epsilon TS. And we have shown earlier, when phi 1 is less than 1, YTS will be stationary. Okay. Now we are looking at what will be the behavior of YTS when phi 1s is equal to 1. If phi 1s is equal to 1, the behavior of YTS will be different. Okay, and in this case, we have a possibility for unit root. If phi 1s, the coefficient for AR1 in seasonal time series, is equal to 1, then we have a unit root. But what is the difference between our conventional analysis for non-seasonal and the analysis for seasonal? In the case of non-seasonal analysis for AR1, you have only one unit root. But in the case of seasonal time series, you have more than one unit root, even in the case of AR1. If you have a quarterly data, you have 4 different types of random walk for 4 quarters separately. So in the case of a quarterly data, you may have 4 unit roots, 4 different types of unit roots. If you have monthly data, you have 12 different types of unit roots. In the case of annual data, you have only one type of unit root in AR1. So this is the basic difference between annual time series and seasonal time series as far as the random walk process is concerned or the unit root behavior is concerned. So in the case of seasonal time series, you have more possibilities of the unit root behavior or the more possibilities of the random walk behavior. Let we try to understand the concepts of random walk in the case of quarterly series first, then we can expand our analysis later on. So this is the AR1 process in general for seasonal frequency S. If we set phi 1 is equal to 1, the expression simply looks like this. After setting phi 1 is equal to 1, we have a behavior what is called random walk. Okay. But here with seasonal frequency S, you have S number of independent random walks. As I have already mentioned, for quarterly data, you have 4 independent random walks for 4 quarters separately. For monthly data, you have 12 independent random walks for 12 months separately. Okay. So let we consider the quarterly data first. So for quarterly data, put S is equal to 4 here. So the expression becomes the 1 minus L to the power 4 y T4 is equal to epsilon T4. What does it imply? YT4 implies value of y in time point t when we have a quarterly data, and random disturbance at time point t when we have a quarterly data. But after putting phi 1 is equal to 1, the polynomial function looks like this, 1 minus L to the power 4. And I have mentioned earlier, if we set this term equal to 0, you have the inverse characteristic equation. Okay, and by solving it, you have a characteristic root. And if the value of the characteristic root is equal to 1, then you have a unit root. Clear? So we have started with phi 1 is equal to 1 in this expression. Phi 1 is equal to 1 indicates random walk. If phi 1 is equal to 1, you have 1 minus L to the power 4 is equal to 0 as a inverse characteristic equation. So here you can find the difference between annual time series and quarterly time series. In the case of annual time series, what would be the expression for this part? Simply 1 minus L. So in that case, you have 1 minus L is equal to 0. Okay. And the value of L is equal to 1 indicates the value of the root is equal to 1. And this is the case for unit root. But in the case of quarterly data, if you set this expression equal to 0, after factorization, you will get this 1 minus L into 1 plus L into 1 plus L square. This part is equal to 0. Okay. If we manipulate further, you will get 1 minus L into 1 plus L into, for this part, you can write 1 minus IL into 1 plus IL. I denotes the complex number, square root of minus 1. So this equal to 0. So if you solve it, you have 4 values of L. So you have 4 characteristic roots by setting 1 minus L to the power 4 equal to 0. Similarly, if you have monthly data, this expression becomes 1 minus L to the power 12. By setting it equal to 0, you have 12 number of characteristic roots. So in the case of annual data for AR1, you have maximum characteristic root equal to 1. But in the case of quarterly data, even in AR1, you have characteristic roots equal to 4. For monthly data, you have characteristic roots equal to 12. So you have more characteristic roots if you have more frequency in the data, or so as you move into the higher frequency, the number of roots will be more, and in that case you have several possibilities as far as the unit root behavior is concerned. So let me look at first the case of quarterly series. So in the case of quarterly series, we have 4 roots. By setting this part equal to 0, you have the value of the roots. L1 is equal to 1, L2 is equal to -1, L3 is equal to I, L4 is equal to -I. And these 4 characteristic roots have 4 different meanings. The first root equal to 1. This is our conventional unit root. Okay, so if L is equal to 1, it corresponds to the 0 frequency. 0 frequency means we are ignoring the seasonal frequency. So when we ignore the seasonal frequency, we have got the similar result as in the case of annual data. So the first root relates to the 0 frequency. The second root relates to the frequency of half of the cycle per quarter. You have quarterly data. So if you have half cycle per quarter, so in a year, you have 2 cycles total. So half cycles per quarter means by taking 2 consecutive quarters, you have 1 cycle. So a year contains 4 quarters. So in this case, you have 2 cyclical movement. So within a 4 quarter movement within a year, you have 2 cycles when we consider the value of L is equal to -1. For the complex roots, value of L is equal to +1, +I or -I. In that case, we have 1/4 cycle per quarter. As we have a quarterly data, we are considering quarter. If you have a monthly data, you need to take into account a month. So in that case, half cycle per month. If half cycle per month, so in a year you have 6 cycles. Okay, 1/4 cycle per month. So in that case, you have how many cycles? If 1/4 cycle per month, so in that case, you have 3 cycles per year in the case of a monthly data. Like this. So in the case of a monthly data, you have more possible cases. For quarterly data, you have 4 cases, 1, -1, +I, -I. If you have a monthly data, this expression becomes 1 minus L to the power 12. So conceptually, you have 12 number of characteristic roots, and 12 characteristic roots provides you different types of movement of the series at different cycles within a year. So the first value of L provides you a 1 cycle within a year. So 1 cycle within a year means 0 frequency, that is it just similar to the movement of the annual time series. The second value of L in our case, quarterly data, provides you the half cycle per quarter. So if it captures half cycle per quarter means in a year there are 2 cycles according to the value of this. So the value of this determines the movement of the variable in 2 cycles per quarter. What would be the movement? What would be the type of the movement of the variable if we consider 2 cycles in a year? That is determined by the value of this. Similarly, the complex roots provides here the behavior of the movement 1 cycle per year, because here you have per quarter 1/4 cycle. So 1 quarter indicates 1/4 cycle. Therefore, 4 quarter indicates a complete cycle. So the 1 cycle within a year, the behavior of the 1 cycle within a year is obtained from the roots I and -I. So these are the complex parts of the characteristic roots that you have got by setting the polynomial equal to 0. Okay. So in this way, we can take into account the more detailed behavior of a series if we have a high frequency data. If we have a quarterly frequency data, we can analyze the behavior of the series by considering 4 roots. That is, by considering 4 kind of cycles within a year. If you have a monthly data, you can analyze the behavior of the series by considering 12 possible cases, 12 possible cycles within a year. Okay, if you have a weekly data, you have L to the power 52. So in that case, the polynomial becomes 1 minus L to the power 52 equal to 0. And by solving it, conceptually, you can get 52 number of characteristic roots. So 52 characteristic roots provides you the behavior of 52 types even within a year. Okay, because a year in that case contains 52 weeks, and the behavior of week 1 may be different from behavior of week 2, that may be different from behavior of week 3, etc. over the years. So in this case, we can get a detailed analysis of the behavior of the series if we look into the seasonal frequency. Okay, have you got my point? So let me stop now for today. Next day, we will directly move into how to carry out unit root test in the case of a seasonal time series. So these are the concepts of unit root in the case of a seasonal time series. How do we get unit roots? You have several unit roots, more possibilities of appearing unit root in the case of a seasonal time series as compared to the annual time series, and accordingly we can analyze the behavior of the data. Suppose you have monthly data for IIP, Index of Industrial Production, or if you have monthly data for CPI, Consumer Price Index, WPI, Wholesale Price Index, or exchange rate in the case of a trade. So you can analyze the monthly time series by considering the monthly behavior over the years. So the behavior of exchange rate in January throughout over the year for different years, behavior of exchange rate in February over the years, and these kind of behaviors may be stationary, may be non-stationary. So non-stationarity, stationarity in the case of a seasonal time series will be of different types. So this is the more possibilities as far as the unit root behavior or the stationarity, non-stationarity behavior is concerned. If you have a daily frequency data, for example, if you are interested in finance, if you want to analyze the Bombay Stock Exchange, BSE Sensex. So BSE Sensex is an important indicator capturing the financial market in our country. So if we want to analyze the financial market by simply just by taking the BSE Sensex, you have a daily frequency data online freely. If you go through the BSE website, you can easily download the data in daily frequency, and it is available from early 1990s till date. So you can get the data till today, and it started early 90s. So it is a long time series. So you can analyze the longer time series to analyze the behavior of financial market in our country. So if you use the daily time series data, in the case of a daily series, you have a 7-period cycle, because Sunday, Monday, Tuesday, etc. In this way, that is the behavior of Monday, behavior of the stock market in Monday, and the behavior of the stock market in Friday will be different. So you may be interested in analyzing the behavior of stock market in Monday only over the year. You may be interested in analyzing the behavior of the stock market in Friday over the years. So the behavior of the stock market in Friday over the year may be different from the behavior of the stock market in Monday over the years. So the behavior of the market, particularly stock market, changes by day, and in financial literature it is called the day of the week effect. That is the effect on the financial market in Sunday, effect on the financial market in Wednesday, effect on the financial market on Friday will be different normally, because you know Monday is the starting day in a week. So in a starting day, there is a lesser information regarding the parameters determining the asset price or the equity price in the market. On the other hand, in Friday you have got more information within the week. You have information from Monday, Tuesday, Wednesday, Friday, up to Thursday. So on the basis of these informations, you can take a decision on Friday whether you will invest money in the stock market or not, and in which equity you can invest. So there are a lot of informations on Friday. That's why the behavior on Friday will be different from the behavior on Monday. So you can analyze the behavior of the Friday of a stock exchange over the years, behavior of the Monday of the stock exchange over the year by using the daily time series data. So in that case, in the case of daily time series data, you will get 7 possible types of random walk behavior. So in the case of quarterly data, you may have 4 different possible of random walk. In the case of monthly data, you have 12 different possibles of random walk. In the case of daily data, like stock exchange, you will get 7 different types of random walks. Okay, so in this way, we can analyze the behavior of the same variable. Sensex, for example, Sensex is our variable. So we can analyze Sensex for Monday only. We can analyze Sensex for Friday only in this way. So these are the basic advantage of using seasonal time series or time series with high frequency data. Okay, so let we stop today. We have a few minutes left for this session, so we can discuss what you want to discuss here relating to the topics we have covered. So let we try to discuss we have discussed till now. বলো তোমাদের যদি কিছু প্রশ্ন থাকে।